Welcome to this talk on visual analytics for understanding Draco's knowledge base. My name is Johanna Schmidt. I'm leading a research group at the VIS Research Center in Austria, and this work was done together with a master's student, Bernhard Pointner, and Silvia Miksch from the TU Wien in Austria. A quick introduction to Draco. Draco was published by Moritz et al. In 2019 and is a visualization recommendation system. Draco recommends ranked visualizations, chart types based on Vega Light, based on a given dataset, and based on a request which parts of the data the user wants to see. Let's see how this works in the online demo. Here a dataset about cars is given. The user decides that he or she would like to compare horsepower against acceleration, and then Draco suggests fitting visualizations. That can also be extended to histograms, for example, where horsepower is visualized, and for strip visualizations. Draco can make these recommendations because it has a large knowledge base in the background. In this knowledge base, Draco stores the rules which define when to apply which visualization techniques. We wanted to know how these rules inside the knowledge base look like, how they are connected, and how they are related to each other. We think that visual analytics can serve as a proper technique here to get some insights into this type of data. Some terms that need to be defined here. Rules inside the knowledge base are defined as constraints. Constraints restrict the recommendation space. Constraints can either be hard, which means they cannot be violated, or soft, which means they might be violated. Draco knows 230 hard and soft constraints, which are arranged in categories. If a soft constraint is violated, which means that the logical expression of a constraint is true, then this constraint generates negative costs for a certain visualization. Visualizations in Draco are recommended and ranked based on these costs. Before being able to visualize the knowledge base, we had to extract relevant information. We applied a data pre-processing strategy where we created an abstract syntax tree out of the logical constraints in Draco's knowledge base. More information on this step can be found in the paper and in the supplemental material. One more term that needs to be introduced here, features. After extracting the abstract syntax tree, we could identify common patterns that occur in multiple constraints. We called these patterns features, and we used these features to identify relations between constraints. These are the research questions our visual analytics solution addresses. Which features are shared by different constraints? How does the distribution of costs look like? Which constraints are violated by specific recommended visualizations? And which recommended visualizations share violated constraints? To start with visualizing Draco's knowledge base, we arranged constraints in a circle in a fixed radial layout. The categories are arranged as arcs, constraints are shown as individual nodes, and costs are mapped to color. Then we integrated our newly generated information, our abstract syntax tree. This tree shows the shared features among the constraints, and these connections are shown as hypergraph in the middle of the circle. The knowledge base is visualized as a hypergraph. Constraints, which are defined in the knowledge base, are hierarchically arranged as nodes in a circle. Hypernodes represent shared features that connect constraints. Our approach is interactive and allows to explore the hypergraph in more details, for example by tooltips or also by zooming and panning and filtering. Filtering means that users can click on a constraint they are interested in, and then only this constraint is shown and the rest of the hypergraph is filtered away. It is possible to go back to the full view of the hypergraph by clicking a button. To use the system, users will first ask Draco for recommendations for visualizations for a given dataset. Then users can hover over the recommendations to see which constraints have been violated. It is also possible to select multiple recommendations, and then all constraints that have been violated by these recommendations are highlighted in the hypergraph. Colors are used to differentiate between the selected recommendations. In the other way around, it's possible to hover over elements in the hypergraph to see which recommendations violate these elements. This is possible for features, so it's possible to hover over the nodes. And this is also possible for constraints. And in both cases, the recommendations that violate these elements will be highlighted. Different characteristics for features are visible in the hypergraph. The feature E is shared by almost all constraints in the knowledge base. Other features are only connected to a few constraints. For example, the feature En, which refers to entropy, is shared only by the constraints controlling varieties of color as well as overplotting. Two recommendations, A and B, have been selected, and the visual analytics system assigned them two colors, red and blue. The violated constraints are highlighted by colored stripes in the hypergraph. It can be seen that the two recommendations, A and B, violate the same constraints. When hovering over a third recommendation, which then gets a gray border, the one constraint, positional 0, not violated by A and B, becomes visible, which explains the additional costs of 2 added to this recommendation. We conducted an evaluation to test the feasibility of our solution. For the evaluation, we employed 3 evaluation methods: observational task performance analysis, a heuristic value-driven survey, the ICT method as proposed by Wall et al. In 2019, and qualitative interviews. The study was conducted over Zoom with video and audio recording. We had 6 participants, and each evaluation lasted for about 45 to 60 minutes. This table shows the evaluation scores according to the evaluation component insight, time, essence, and confidence. According to Wall et al., an average value greater than 5 is considered a success. Participants showed good scores for time, followed by insight and essence. Confidence was rated low, which shows that the participants would have to familiarize themselves with the topic and the visualization more. In summary, we saw a steep learning curve and many aha moments. Participants quickly gained insights for the tasks we gave them. However, we also noted confusions at the highlighting of the violations when checking recommended visualizations. And we also see potential for improving the interactions and the filter operations. Our contributions consist of a visual analytics approach to explore Draco's knowledge base and a tooling to explore and retrace the violations of recommended visualizations. The feasibility of the application was proven in an evaluation study. Our application is online. There's an online demo available, and we also published the source code on GitHub. The URL is on the slide. Please check it out, and we are also very happy for feedback. Thank you very much for your attention.